Okay, good afternoon, warriors. I'm gonna try doing a video session right here, and we'll see how that goes. And if it's good quality, I'll get it out to you, and we'll go from there. So first things first, let's start like we normally would. Let's start with a little map check. All right, so here we are today. We've got sampling solo drives out there that are never due. And those are just for you to do and ask me questions on. I do want you to do them. That is very important. You're assuming a lot of risk if you do not. Um, also, we are on Sunday, no later than 11:59. Pearson validation assignment to Bravo is due. And then looking into next week, right now we've got scheduled mandatory Zoom on Tuesday during our normal class time. And then we'll go into confidence intervals on that day. And then I'm still figuring out what Thursday, the 26th of March, looks like. Potentially do some sort of reverse solo drive or a we drive in Zoom, but I've got to figure that out. So I owe that to you pretty quickly. And then next Sunday, not this coming, but next, we'll have all Pearson due. Everything that's on Pearson from block number 2 will be due. And then the following week, so 2 weeks from today, we'll have an exam. So figuring out what that's going to look like, more to follow. So in this video session, I want to talk about some things. I want to review why we sample, and it's important that you watch the sampling video if you have not. Really the video on sampling probability. We're going to talk about the importance of sample size on probability, the effect of that has on probability. And then we'll talk about what proportions are going to sample proportion probability. And then finally, how and more importantly, why to model these problems like a mother in Excel and what the value is there, both sort of tactically and strategically. So I'm going to go to, I have a little whiteboard here. It's not the greatest, but it's okay. So I'm going to go to that. Okay. So first of all, why we share in, or excuse me, why we sample in the first place. And really we sample for two reasons. Um, One is because we know how the population is supposed to be functioning. We have an idea about how things are functioning, and we want to see in our little piece of the world how our piece of the world is functioning compared to that population. Okay. I'll just put this right here. And so to do that, we take a sample. So this might be all of the college students in the world. So something like the mean weight or the mean academic performance or the mean something of all college students in the world is that. And so we take a sample to see if we're any different or we're kind of in line with that. And so we take a sample X bar over here. So what we want to do here is see, hey, are we performing in line with that or are we not? Are we different? Is something different occurring over here? And maybe something is different occurring here. We just haven't detected it yet. Another example of this is in production. So, if we're supposed to produce, like I talked about in the video, bottles that are 500 milliliters, and we sample here and we find out that it's not. So, that's where the probability comes into play because, again, probability is the likelihood not only that something is occurring in the future, but the likelihood that something would be occurring right now. Now, here's the trick. Um, we we have knowledge of how the population is supposed to be performing, standard deviation. And so we get a sample and we look at the probability of that sample indicating that our sample is performing as the population would. So, in other words, if our probability is very low here, then one of two things is going on. Either we have too small of a sample size, n, and we'll talk about that in a second, or something has changed. Something is off. Something might be wrong if we're doing a production process. We're supposed to have 500 milliliters, and the sample of the probability of our sample mean is so low, it indicates that we're not behaving in accordance with this, that something has changed. Maybe our production process is off. Um, so, but if the probability is high, that means that things are occurring in accordance with this over here. And that is very key. That may not come to you, this concept may not come to you right away, but this is definitely something that you need to struggle with until you feel comfortable with what we're doing. The other type of sampling, which we're not going to cover this week, but we are next week, is where the opposite is going on, where we don't know what the population mean and standard deviation are. And so we have to sample so we can get a guess of what that might be. And this is more like where sometimes these go hand in hand. So we may have a notion or a belief or a standard of how the population is supposed to be behaving. We take a sample and look at the probability of that sample mean occurring. And if it's low, let's say it's very, very low, and our n is high, which means we have a really good sample, we might take that information and make the temporary conclusion that the population mean and standard deviation have changed. And therefore, we're going to use our sample information to take a guess on how they have changed. So, this will be next week. This is what we're working with in this week. Sorry. I don't know what's going on with that. Okay. Seem to have lost my whiteboard. What's up with that? Okay. And perhaps I'll clean this graphic up a little bit, make it clear. So um, let's talk about the importance of sample size. So let's suppose that we have a very small n. Okay. Well, first of all, we always have single value x, but just in the name, single value x and knowing the probability of single value x is fine if we're trying to predict a single event occurring, or less than or more than or kind of a between kind of thing. So, like we talked about in the one last ride you drive, when will the truck arrive? That kind of thing. When will the shipment arrive? And that's fine. But when we're looking at statements about the population mean and population standard deviation, and we're looking at X bar, the sample average, then sample size starts to play more and more of a role. So we have what's called central tendency and the theory of central tendency, which means that, no pun intended, the higher n becomes, the larger that sample size becomes, the more our distribution will tend back more towards the mean. Okay, let's just slow down a little bit and make sure we understand what that means. Let's suppose that we have a very, well, first of all, let's just talk about in practicality. So, in one of my other classes, I've got a warrior named Riley. Riley plays on a basketball team. Riley is a very tall dude. So, if I was trying to collect a sample of the heights of York College males, and I took Riley and another male warrior, and I took the average heights of them, well, my overall sample average would probably be pretty high. Okay, Riley is really going to throw that average off, so to speak, because Riley's probably about 6'7". But if so this would be X with a low N. But if I take Riley and I take the height of some other males, and I know this drawing is just so compelling. It's just breathtaking, really. So the more I put into my sample size, probably my sample mean is going to go down. It's going to decrease. Okay, because Riley's not going to be able to throw it off as much. The rest of these folks are going to even it out. So what does all that mean? Well, let's take a look at what the probability curve looks like for this situation right here. So let's say n of 2. Well, n of 2, my distribution is going to look a lot flatter. It's still going to follow a normal distribution, but the probability of a sample average, let's say, let's just put this in inches. If Riley's 6'7", that's 12 times 6 is 72 plus another 7, 79. I think I got that right offhand. And then let's say this guy's like 6 foot, so he's 72. And I'm just guessing. So let's say that average is like at 76 is the sample average. And I want to say the probability is 76 or greater of that sample average. Well, I'm going to be probably out here somewhere, and I'm going to be looking at this area. Would be that probability. Okay, so whatever that is, it isn't that great. We know it's a low number, and that's fine. But over here, when I have an n, and here I have an n of 2. Over here, I have an n of 1, 2, 3, 4, 5, 6. Well, even with that slight change, this curve is going to be more taller in the middle and lower on the outside. So it's going to go back in toward the mean, which is right here. Okay. And the more we increase, so if we take another sample of, let's say, so this would be N2, this is N1, that curve right there is this one here. This curve over here is this one there. Okay, so let's say we take another curve, N of 3 of like 20, and this thing's going to scrunch in even more. Okay, so with each time, you know, our sample average is going to be closer and closer to the mean, assuming that our sample average is behaving the way that it would in accordance with the normal distribution. If it's not, then probably our population mean and standard deviation is off. And that would be this piece right here. Okay, which would really mean that our mean has moved, which is where we do something else. But for now, we really want to see, okay, what that probability is. So that is the effect. The point of this whole diagram is to show the effect on sample size. As sample size gets greater, the sample averages and the sampling distribution should go closer and closer to the mean each time. That is the rule of central tendency, so to speak. Okay, shifting gears now to proportions. Okay, so first of all, what is a proportion? Well, we don't have a single value proportion because there's no such thing. And the definition of any proportion is we have n in the denominator, and then we have the characteristic of interest in the numerator. And this really lends itself well with categorical variables, which we haven't talked about in a while. We've talked about numerical variables, speed, weight, distance, time, those kind of things. But we haven't talked about how many people like Billy Idol, for example, or how many people would like Popeyes, for example, or how people feel about this presidential candidate versus another one, for example. So here we have our friends. If we think about our last tattoo, I told you we would have it again. So we have a sample, and we know that for the mean, we have the mu and we have x bar. And for a new friend that we're going to run with is proportion. And here we have that, which is not pi. We're going to call it p pop. So you're going to see me write about p pop and solo drives and other things like that. And within the sample, we have just plain P, although again, we need context and need to realize that that's what that is. Okay. So P is going to be the characteristic we're interested in. Um, if people like hot dogs, if people are interested in Metallica playing at YCP, and then the number of people that we talked to or that responded to a survey. Um, and so we need to think broadly. This could be a yes or no question. Would you like Metallica to come? Yes or no? This could be, would you like Metallica or Slipknot? And so X is maybe the amount of people that wanted Metallica. Um, and we know that if we ask folks Metallica or Slipknot, that adds up to N. And so the people who said Metallica so N minus the people who said Metallica equals the people who said Slipknot, assuming that we only offered two choices. Um, so these are all proportions. And proportion, just to beat a dead horse, comes from the word portion, okay, which means mathematically less than one. If this is 4 and our sample size was 5, then we know that P is going to equal zero 0.8, for example. Okay, so that's a big tip, one of those ice cube things. Check yourself before you wreck yourself. That if we're working proportions and we have numbers that are less than one or more than one, it's probably not a proportion. Now, tips in a narrative. Well, how do I discern whether a problem has to do with the mean or the proportion? Well, number one, are we talking about a numerical continuous variable? That would be more like a mean kind of problem. Or are we talking about like a categorical variable? That would be a proportion kind of problem. Um, Although we could have numerical proportions, it's not just categorical, but they're discrete. So, for example, let's suppose that I'm tracking, even with our previous problem on production with bottles. So, I'm measuring how many bottles are 500 milliliters plus or minus 0.25 milliliters of standard deviation. And so I'm counting how many fall outside that range. Well, those would be errors. And so I might take a sample size of 5 and find that 4 fall out of that range. So those are, I don't have zero point 0.2 of an error. I either have an error or I don't. Or to make a simpler example, let's suppose that I'm producing tables. And so a table either has an error on it or it doesn't. I can define error in a number of different ways. It has a scratch, it has a blemish, something like that, or not. Um, but that's how that would look in terms of proportion. So that's P is our sample proportion. Now let's do this again and kind of tie it back to everything we've talked about. So same type of process. Remember our diagram recently. So we know something about the proportion of the population, which would be P pop. And we want to see if in our piece of the world that P, the sample proportion that we take, we want to see the probability of that sample proportion occurring. And based on that, we're going to make a decision that either our piece of the world is behaving kind of in accordance with the larger population or it's not. And if it's not, either we're different or something is wrong or this is false, then we would kind of go down here. So, how do we do all that? What are the formulas? This is the process. We're going to talk about this portion again next week. We're going to talk about this portion right now. Okay, so if we're going from the population, we need to know what that is. And in a narrative, we might have something like every 4 out of 5 people. We might have, so just do this. We might have 4 out of 5 people. We might have 80% of people prefer hot dogs over hamburgers. We might have 4 out of 5 people prefer Coke over Pepsi, those kind of things. The first step is just to get and compare apples to oranges. We need to convert these to a decimal. We're going to need to do that. Okay. Now, as far as our sample, we need to know N and we need to know the characteristic that we're interested in. Okay. So, and N is going to be more than, and so P is going to be equal to X over N. Again, if this is some kind of statement that 4 out of 5 or 80% of college students prefer pizza over hamburgers. And we want to see if your college is any different. So we would go around, we would go sample some folks. Same concepts apply. The higher the sample size is, the more we have an idea of tendency, but it's a little more complicated than that. But we'll leave that for now. Sample size, bigger sample size is always better. That should work for you. So let's suppose that we take a sample size of 50 people and we find that 10 are interested. So our P would be 0.2. So the question then becomes, what is the probability of that proportion occurring if our selected area is performing in accordance with the population proportion? Now, here the formula is a little clunky, but the process is the same. We know that this is not a probability, nor is it a z-score. To find a z-score, we're going to lead with p, and we're going to subtract by the p-pop. Now, the denominator is actually the standard deviation of p. We're going to take p-pop, and we're going to do this, and then that. So in this instance, we would take 0.2 minus 0.8, and then we're going to take all this stuff in the denominator. We know 50 goes down here. We know 0.8 times 0.2 goes there. And we know this is going to be a negative number out here. I am going to stop this video for now, but I'm going to pick back up with this example, and we'll close this thing out.